All right, I think it's half 5 past, so very happy to have Zhongweiyang Xu joining us today to talk about diffusion models. This is probably the most ML topic right now for this particular talk series, and you know it's also a hot topic overall. So we're very happy to have him to be talking about this. Zhongweiyang is actually right now a PhD student, very close to finishing up, working with Romit Roy Chaudhuri, and then he's mostly working on the theory side and also with applications to speech processing. So we're very happy to have him just talk about diffusion models. Yes, Zhongweiyang, take it away.
Sure. Thanks a lot. Yeah, so I'll just start. So today I'll be talking about unsupervised array speech processing with diffusion as a foundational part. So yeah, so we have done on this area for about like 1 year and have some recent progress on this. So I'll basically so this is today's outline. So I'll first present our like recent paper called ArrayDPS. So array means microphone array, DPS means diffusion posterior sampling. So yeah, so it's doing some unsupervised blend speech separation with a diffusion prior. And so everything today will be built on this the framework proposed in this paper. And then like if time permits, I'll discuss our new WASPA paper called USD-DPS. So unsupervised speech dereverberation, that's USD. So unsupervised multi-channel speech dereverberation by diffusion. And then like I'll like briefly talk about what we are still doing and what are the potentials and limitations for this kind of algorithm. Sure. I'll first start with our like this paper, ArrayDPS. And yeah, so I'll discuss the background and motivation of this paper. So we focus on the cocktail party problem, and we want to separate multiple speech sources given a multi-microphone recorded mixture. So like multiple speakers are talking simultaneously in a cocktail party scenario. So S1 tilde and S2 tilde means that those signals are perfectly clean and anechoic, and to be recorded, they need to travel through some of room impulse response channel. And G11 means that it's from first source to the first channel, and G12 means it's from first source to the second channel, and like so on and so forth for the other speakers. And those speech recorded at different channels, they add up with noise to give you the first channel noisy reverberant recordings. And we sometimes call it we call it reverberant mixtures. So Xi, Xj corresponds to the mixtures at J's mic, and Nj corresponds to noise at the J's microphone. And Gij is the IR from I's source to the J's microphone. And Sij would be the like reverberant source image. We call it reverberant source image recorded at J's microphone from source I. Right, so those are the notations and the problem setups. Yeah, so like in general for this separation problem, what the system's input is this multi-channel mixtures, X1, X2 in our case, 2 channels. That's just for this figure. And the output would be the S1 tilde and S2 tilde, basically the original clean signal. Yeah, and actually for this paper, I should clarify that like whatever we are separating, we are actually separating this source image S11 and S12. All right, and later we'll have more clarification on that. Yeah, so most existing methods, there are lots of methods on like multi-channel source separation today, and based on neural network, the performance are really good. But those methods, like they still have a few problems. I'll just list it there. So first is that they are supervised. So like if you train those neural networks on speech enhancement separation, you have to train on simulated dataset. And those datasets are simulated using simulated room impulse responses, using image source models. And I mean, those IR simulation, they might have some difference from real world IRs. Yeah, actually, if you look at the real world RIRs shape and the simulated RIRs shape, they're quite different. And other thing is that acoustic transfer functions mismatch. So like the microphone array might be mounted on something and that would change the acoustic transfer functions, like when the certain directional sound arrives at the microphone array, right? It might not be like perfect. It might not be perfect, those delay and some, but the delay kind of channels between channels. And yeah, so so one example is that you can have a AR glass mounted on a human head, and that human head, like different kinds of human heads, they might have different filtering effects, like HRTF, those things. That would cause some generalization issues. And second of all, those models are mostly deterministic, and we usually call those models predictive. So given any multi-channel mixtures, they directly output a deterministic solution, and it's usually optimized in MMSE during training. And those kind of, if you're optimizing MSE, like sometimes we call it regression to the mean. So like the optimal solution would be the conditional expectation, right, of the posterior. So so assume that given all of those multi-channel mixtures, you can have lots of possible like sources that would all sum up to those mixtures. And if you have lots of possible solutions, what optimal MSE solution would give you is to give you the mean of all of those possible solutions, which can be very blurred. And that causes lots of distortion. And that happens a lot in low SNR conditions where some of the speech are masked by noise. And in that case, you really need something that's a bit generative, not something that's a mean of all the possible solutions. Right? And third, like lots of models, they are trained or like assumed fixed microphone geometry. And so if you want to like have a model that works on any other microphone geometries, it's not going to like work well. And you need to train like any different microphone geometry and to train another model. So those are like a few shortcomings of existing methods. So we are proposing this ArrayDPS, which is a Bayesian approach, which is unsupervised, generative, and array-agnostic. We want to bypass all of those previously mentioned problems. So in a high level, ArrayDPS, it samples from the posterior distribution. So S11, S21 are basically the source 1 recorded at first mic, source 2 recorded at first mic, and source K recorded at first mic. And we want to sample from all of those sources given the multi-channel mixtures. And but how are we going to sample from it is basically our main focus. So to do that, we use a Bayesian approach, which means that we just apply a Bayesian rule on this posterior, and we don't need to care about the denominator because it's unrelated with those sources. So we can just decompose the posterior into like a few prior terms and the likelihood term, just like any inverse problem. And so it can be decomposed into source 1's prior, source 2's prior, source K's prior, and the likelihood of the mixture given all of those sources. Yeah, so ArrayDPS is trying to like sample from this distribution, like by using prior models and likelihood models. And previous works, mostly classical models, they usually focus on likelihood, right? So if you look at very like old methods, EM-based methods, or like IVA, ICA, those kind of methods, they usually assume very weak priors. So sources are independent, and sources, they have some Gaussian in STFD domain or time domain even, and Laplace, also Laplace assumptions on the signal maybe, and some methods, they use some like learnable NMF prior, and that's like strongest prior that people usually do for those classical models. And so what we do is that we use today's diffusion model to model the speech source prior, and that's quite a game changer for those kind of Bayesian models. And Yeah, and of course, we also use a signal model for the likelihood. And because we are using diffusion, so the signal model, we need to design it carefully to fit into the diffusion framework. I'll give a very quick background about diffusion models. So what diffusion model does is that it defines a fixed forward diffusion process. So it keeps adding white noise to a clean image. So clean image are from a clean data distribution. And diffusion process basically keeps adding noise, define a process that keeps adding noise to the clean data. And ultimately, the clean data distribution will become a distribution of Gaussian noise in the end. And so the forward process can be described by something called a stochastic differential equation. And the F term here usually is called drifting term that as time goes to the right, we become more and more noisy. So the tau is increasing, the S will be like shifting towards this direction and with some added noise to it. And like what people developed is that by defining such a forward process, and people, if you are going to try to learn to reverse the process, people basically learns that you can just train a neural network to do MMC denoiser from any time diffusion step, and then you are able to do the reversal diffusion process following a reversal SDE shown below. So F and G, those things are predefined. And so what the neural network is learning ultimately is this a gradient S log p tau S, which is a score function. And so the neural network has access to this score. And then neural networks is also doing like denoising. So basically the score and the denoising function, they have some close relationship, which is usually called Twitty's formula. And so what this says is that we can, like when the data distribution is totally Gaussian, we can directly sample the Gaussian and then follow this reversal SDE process to gradually decreasing tau and gradually denoise it, and finally get back to the data distribution. So that's how diffusion model is able to sample from like data distribution. And though this term is so this SDE is stochastic, and there's an equivalent version that allows you to sample exactly the same distribution by following ODE. So there's no such stochastic term here. So this dW here and dW here, they are like the winner process. It's like d tau multiplied by some Gaussian, by unit Gaussian. And that process, it happens both in the forward process and in the reversal process of the SD. But there exists the equivalent ODE that allows you to sample without this stochasticity. Yeah, so we are able to sample from the noise, and after that, everything is deterministic. It will directly give you one data sample. And so following this ODE, we are able to sample from the any prior distribution the diffusion model is sampling. So like any questions so far?
Good.
Okay. Good. So sure, let's move on. So yeah, so in our project, we are trying to have a diffusion prior, a generative prior to model the source clean speech, PS. So this is a like ODE with some simplification from the previous slide. It's just for some like for some specific setups of the F and G functions before. And let's just assume that we can use this simplified ODE for sampling. And so what we need is that the sigma tau is related to the G before. So it's like we predefine the schedule, diffusion schedule. And to sample from a clean source speech, what we do is that we start from a very noisy sample, and we follow this sampling ODE. And after like a few hundred steps of solving this ODE, we get a clean image of S0. And what's needed in this ODE is this score function that's approximated by the neural network. And so here I have some quick thing about how the diffusion model is trained. So what it does is that it keeps sampling from the clean image dataset, clean image distribution, and then add some diffuse noise to it, and learn and trains a denoiser, diffusion denoiser, to like denoise in a MMSE manner, right? And then after it's trained, like the score function that we need, it can just be approximated by this function. So this should be equal sign if this is perfect MMC denoiser. Okay, so that's something that can build between the score function and the diffusion denoiser. Right. Yeah. So now we know that we have a diffusion model as a prior for the source image for the source speech PS. So we are able to sample from PS. But what we focus on is inverse problems, like separation, enhancement, dereverberation, those kind of problems. Yeah, and I'll first talk about this paper called Diffusion Posterior Sampling that kind of defines a framework to solve inverse problems. And in this problem, what they define is that x is equal to as plus n. And you can think of s as some like clean speech sources, and a is a distortion matrix that would sum up things and distort things, and n is the noise, and x is the recording. Right. So the goal is always to recover s from x. And in their setup, they are assuming that A is a known system matrix. So A is known, that is important for their assumption. And N is noise. So what we want to do is to recover the plain speech given the distorted mixtures, right? So we want to sample from PS given X. So to sample from PS, it's simple, right? We mentioned before that we have already trained a diffusion model to approximate this score term, and then we can solve the probabilistic flow ODE, starting from a very noise, from a Gaussian noise. We're able to sample clean speech using this. But what if we want to sample from PS given X, which is what is defined here, right? And so, I mean, it's straightforward to say that, to sample from PS, we follow this ODE. But to sample from PS given X, we follow this ODE, except that the score term, the prior score term becomes a posterior score term, right? So we need this posterior score term, but we don't have access to it. And one way to solve it is of course, try a conditional diffusion model. Directly feed this X mixture into the model. But then that needs some paired data for supervised training, right? So what DPS proposes is that this posterior score, the score of log PS tau given X, we can just run a Bayesian rule on it and decompose into two components, right? So the Bayesian rule's denominator, if you apply the Bayesian rule on this probability, the denominator will be removed because it's unrelated to S tau. And then what's left is basically the prior score, which is shown here, right? So that thing we can have a pre-trained model for that to model clean speech priors, right? So that's directly solved. What's left is basically the likelihood score, which is gradient S tau of log P tau X given S tau. And that is a bit problematic because we are unable to directly have this value. And the reason is that Px given S, if tau is equal to 0, that is fine. We know X is equal to As plus N, and we know the probability graph. So it's totally tractable. A is known and is some noise assumed. So Px given S is known. But here, like on this like condition is S tau, which is a noisified version of S. And that means that it's intractable. Like to calculate this kind of probability, we need to normalize. We need to normalize through all of the possible S zeros because X is a function of S, and S tau is also a noisy version of S, right? So that means that to calculate this, we need to normalize all of possible S zeros, so it's intractable. So we are trying to, so like the goal currently is we want to approximate this this likelihood score, like shown this intractable term. And and one thing that we know is that y is equal to I think I did some typo here. So this should be like x is equal to as plus n, right? This y should be x and this x should be s. So we know that x is equal to as plus n, and A is a known matrix. So basically we know Px given S is the analytical Gaussian, right? Because N is assumed to be Gaussian noise in this case. So Px given S0 means that it's clean. We can directly write it in this form, like simple Gaussian, right? And note that diffusion model itself is an MMC denoiser, right? So whatever we have here is S tau, but is it possible for us to like denoise S tau to be S0? Yeah, so one thing we can do is that we can denoise this S tau to be some pseudo S0 we call S hat 0. And it's not going to be a perfect denoiser. It's too noisy, so whatever you get is also like a very blurred sample, but maybe it's fine for us to approximate this score term. And so what we do is that what DPS does is that we can first denoise using this diffusion denoiser because we always have access to it. And then we can put this S hat 0 into this likelihood function, right? And then like everything is totally tractable, right? We can just take the gradient over the log likelihood function. And one thing we need to pay attention is that we need to backpropagate through this S tau through S hat 0, and S hat 0 is a denoiser function of this S tau. So we need to backpropagate through this denoising, right? So that is that might be a bit tricky in terms of GPU memory and stuff, right? So that is how diffusion posterior sampling approximates this likelihood score term. Yeah, so far so good. Okay. Yeah, so one question is that we are focusing on this kind of cocktail party problem, and we want to we want to try to do source separation in this paper. Yeah, so for source separation, like in the system in the framework of x equal to as plus n, the original source, the original signal that we want to recover, which we call S, is basically the k sources. We can view it as this S1 tilde and S2 tilde. And the X, which is the observation, the mixture that we have the access to, is the multi-channel mixture. But here, like different from DPS, A is something that's unknown. It's a filtering and mixing system as shown on the right. So all of those clean sources need to go through A to be recorded at X, but those A are related to this RIRs and mixings in this figure, right? So if you look at the sampling ODE that allows us to sample from the posterior of PS given X, all of the possible sources and the mixtures, this is ODE. And we need to also approximate this posterior score. And of course, the question is, can we directly use diffusion posterior sampling? So decompose this using Bayesian rule and get prior scores for each of the sources and get the likelihood score using the approximation before. But the prior scores are fine. We can still have a speech prior diffusion model to approximate all the prior scores. But the likelihood score, the problem is that A is unknown, right? So previously in DPS, what they assumed is that this likelihood model, x equal to A is known, so everything is good, can be tractable here. But in our case, A is unknown, so it brings one more level of intractable, because to actually approximate it, we also need to like normalize through all of the possible A's, and that becomes very infeasible. So yeah, so what are the parameters of A? I think we already mentioned this, is that it contains all of those RIRs of different sources to different microphones, right? So C channels, C microphones, and K sources. So a total of C by K microphone, C by K room impulse responses, right? So if A is unknown, then what can we do? And so the intuitive thing is that let's estimate it at some point inside the diffusion posterior sampling process, right? So what we do is that we want to estimate in STFT domain using some trick called forward convoluted prediction. Yeah, it's not as scary as it sounds. So it's just kind of like a winner filter solving process, right? To solve the best filter that matches the signals and the mixtures, right? So remember that at each time diffusion step, we have that S tau, and that S tau of all the sources, we are able to use the MMC denoiser to denoise it to be S hat, right? So the first source is denoised to be S hat. The 0 means that it's clean. It's denoised to the first diffusion step, it's clean, and the K means it's K sources. So we have a rough estimate of the clean speech at any time diffusion step, right? So those things we have. So what we can do is that, is it possible for us to find the best room impulse responses, the IR in the time frequency domain, so that after filtering and sum, they would conform to the mixture the most. So this is what this equation is talking about. It's like solving those room impulse solving those IRs in a maximum likelihood manner, right? So, and it turns out that forward convoluted prediction is exactly doing these things, right? And because everything is linear, the filtering process, everything is linear. So this optimization problem can be directly solved by a linear problem with analytical solutions, right? So the G hat K, this 0 to C is something. C is we are solving the IRs for the C channel, and 0 means that we are sampling some virtual source. That concept I'll discuss a bit later. So here is basically estimating the IRs, and so we are trying to like minimize this kind of like weighted least square. Those weight are purely empirical in this case, and the loss here is basically we want to find the filter that after filtering with the K source, it will match the C channel mixture the most. Yeah, and the reason why like we are not summing all of different sources and then match it with the mixture is because all of other sources are totally uncorrelated with this source, so it doesn't matter. From orthogonal principle, we know that this is already like enough to if we are using learning a filter that best matches F to X, it will only match the correlated part. So that will give us a correct IIR anyway. So that's kind of a trick in this FCP. Yeah, and I'll briefly talk about this virtual source assumption. Yeah, that part is might be a bit tricky. So like any questions on that? Okay, good. And we also have that virtual source assumption. As you can see that we have this G from 0 to 1 and G from 0 to 2. And that 1 and 2 means that it's the channel that connects source 1 to the first channel, and 2 means that it's connecting from source 1 to the second channel, right? And that 0 means that we are sampling a virtual source. We are assuming it to be a channel 0. Right, so that's the assumption we are doing. And the reason lies in that, why do we have this virtual source? And one reason is that if we are going to sample something, we are not guaranteed to make sure that we are sampling the original source signal, because if the source signal is a bit shifted, it can still like propagate through some channel and record it at S11 here. So we don't know like what is the original source signal, so we just define it to be as a virtual source. Right, so those virtual sources are assuming it to be some anechoic clean speech that we are sampling, right? But we don't know like which is the aligned version of it. That's why that we define that kind of virtual source. Yeah, and yeah, someone would ask like, why not just sample this S11 and S21, like just on the reference channel, and then try to learn the relative IIR from S11 to S12. And for that case, it's much more difficult for filter estimation, because the filter you estimate from S11 to S12 is actually some kind of a uncausal filter. You need to reverse back this RIR and then go through this RIR. So it's a bit more tricky process than that. And we have some applications on that later. So this part might not be that important, but it's some like small trick we use in this paper. Yeah, so the overall pipeline is kind of this figure. Yeah, so it's definitely not a very clear figure on how the system is doing. Yeah, so I'll explain. So this is sampling ODE. So what we know is that by following this sampling ODE, we are able to like start from some random noise, and following this noise is the diffusion ODE denoising step by step. We are able to get the output separated sources. Right. And then the problem is in the ODE, there is this posterior score term that we need to solve. And how do we get it? It can be decomposed into like the prior scores and the likelihood scores. I mean, for both sources, we are doing them at the same time, right? And then like for the prior score, what we did is that at time diffusion step tau, S1 tau and S2 tau, to feed into the diffusion unit, it will output the score, right? And in the same time, they will also output the denoised result, right? And the denoised result and the score is just a scale shifted version, right? And by the Tweedy's formula. And then the denoised S1 hat and S2 hat, they were used to feed into the log likelihood approximation. So the approximation log likelihood, we will calculate the log likelihood of this X1, X2, those mixture signals. We will calculate that along with those S1 hat and S2 hat. And so what's happening inside this is something that filter estimation and calculating how much X and all of those filtered sum signals are. And this after the likelihood is calculated, it needs to be backpropagated through this S1 tau. So S1 tau is here, so it will backpropagate through here and get that gradient and directly feed back to this likelihood score, and which will contribute to the posterior score, allows you to do one step of diffusion sampling, posterior sampling. And this log likelihood approximation is basically like the signal model that we are proposing, that we need to estimate the unknown RIRs, right? So the multi-channel mixtures and the sources are feeding to this relative RIR estimator. We are finding an RIR that would after filtering the sources, that would fit the mixture the most. And we got all of those channels RIRs for different sources, and then we filtered them, and we got those estimated source images at all channels, and they would sum up to some like estimated mixtures. And then those estimated mixtures will be compared with the actual mixtures X1 to C, and giving us some kind of likelihood, log likelihood, right? And that log likelihood will just be used here for the to backpropagate through that S1 tau to give us a likelihood score. So that's like the overall framework of ArrayDPS. So far, so good?
Can I ask a quick question?
Sure.
When you say backprop through the diffusion unit, are you considering all the steps of diffusion, or is it just one single unit?
It's one single forward, one single denoising.
So it's not considered the entire diffusion steps.
Yeah, that is impossible. It's very difficult.
Right. Okay.
Yeah. So like if you look at this thing, basically at diffusion time step tau, it's getting denoised. It's getting denoised to the clean signal at diffusion time step 0. So it's one step denoising.
Okay.
This is a unit forward. It's not a whole diffusion process. So the whole diffusion process is here. So we just run MMC denoiser on that, and then use that to calculate the likelihood, and then backpropagate through that denoising unit. Yeah, that's about
Thank you.
that. Yeah. And and then if you think about this algorithm, ArrayDPS, what we did is that at each time diffusion step, we need to, it's kind of like we update the speech source at one step, and we get the next steps S1 tau and S2 tau. And after updating S1 tau and S2 tau, we need to use those for filter estimation here and get the best IIR at this time's diffusion step. And then use everything to update the next steps S1 tau and S2 tau, right? It's like an iterative nature of updating the sources, updating the filters, IIR filters, and then updating the sources. And so like it has a deep connection with expectation maximization, and it happens like when there are some latents that's unobserved. In our case, it's the RIRs, right? And so what EM does is that when it has some unobserved, it keep estimating the distribution of the latents, unobserved latents, and then based on distribution of the latents, it runs the maximum likelihood based on that current estimate of the latent distribution. And then like does it so on and so forth. So latent update and likelihood update doing at the same time. And so it's kind of a greedy nature. Like every time I optimize the best latent and use that latent to optimize my current likelihood. And so sometimes it stacks in local minima. And EM also like, yeah, so EM is very sensitive to the initialization because of that. Like if you have some good initialization, it will give you something that's very close to global minima. And if you have some bad initialization, you are getting to some local minima. K-means is like that. So ArrayDPS also have that kind of nature. So it's also sensitive to initialization. So without a good initialization, there's a chance of failing of this algorithm. Like whatever, like I talked before, that algorithm we designed. So what we did is that we still want to make sure the algorithm is unsupervised. So what we do is that we use some unsupervised classical algorithm to act as the initialization. So that's a bit like cheating, but ultimately everything is still unsupervised. Yeah, that's very interesting. Yeah. So we use IVA. What we did is that we use IVA to first process the mixture, and we get some rough separation estimates, right? And then those rough source estimates, we can use it to initialize the diffusion process. So initially we are starting from the very noisy, like the Gaussian noise, and then denoise it. But in our case, like we use IVA separated outputs and add some amount of noise on it. So not from pure Gaussian, but from some like a noisy version of the IVA separated results. So it's not like we directly start the diffusion process from time t. We started from like t divided by t divided by 2 or like that. We call it warm initialization. And it's not just that. So IVA with some initialization, it can even bring some. We can use those IVA to get a rough estimate of the IIR filters. And then we can use that IIR filters to like guide the first few diffusion steps that are very unstable. And so that would make everything that perform very well. So in our case, we have about 400 diffusion steps, and we use the first 100 diffusion steps. We use the IVA estimated filters as guidance. So like in those diffusion steps, we don't even need to estimate the room impulse response at each time diffusion step. Right? And then for the later 300 steps, I will give the freedom. I will give the algorithm the freedom to estimate the best IIRs so that it can converge like to the global minima, something like that. And so, so what this shows here is that if we are running ArrayDPS with initialization, IVA initialization, the performance is fairly good. If we do not run it with initialization, what happens is that the mean of the separation result is not as good, and it has a very high variance. So sometimes it works, sometimes it does not. That's basically what this metric is saying, right? And yeah, one other thing that's noticeable is the prior. So what's the difference between using an anechoic speech prior and a reverberant speech prior? So this is something like we discussed about why we use a virtual source here. And if we use the virtual source as an anechoic prior, so all of those IIR filters, we can estimate it as causal filters, right? And if we use a reverberant prior, it's basically estimating estimating those relative IIRs from reverberant image source one to the reverberant image source one in second channel. And that is some difficulties when estimating those relative IIRs. You need to reverse back, and reverse of IIRs does not always exist, right? There can be zeros in IIRs and those things. And also brings like uncausal filter estimation. Yeah, and so it also brings some better performance if we use anechoic prior comparing with reverberant prior. Right. And we have some two-speaker results on fixed microphone array, 3-channel. The performance looks fairly good. So yeah, so we should mostly look at ArrayDPS A, which is the default version. And ArrayDPS A max is that so for each method we sample 5 times because they are sampling based method. So we sample 5 samples and calculate the mean and STD. And max means that we just find the best metric from those 5 samples. And ML is that we try to find from those 5 samples, we find the one with the best likelihood. And it's valid algorithm because like to get those metrics, we cannot just get the max, because to get the max, we need to know what's the metric and need some reference. But the maximum likelihood, it's not that cheating because we know the likelihood, right? We know the mixture, we can calculate the likelihood. So it would give us some good numbers. It's a good trick to push for the numbers for those sampling based algorithm. And so you can see that in terms of SDR and SISDR, it can somehow beat the supervised SOTA methods, right? And in terms of SDR, SISDR, but not in Pascal story. And we also have 3-speaker results. And actually, like this result, we did not have it, but because of the reviewers insisted, we make up all the experiments. And surprisingly, it performs much better than supervised best models. Yeah, so that is very interesting. Like we don't even need to use this maximum likelihood of the 5 samples. We just directly sample, and on average, it performs better than supervised model. Quite surprising result. Yeah, and so any questions on this ArrayDPS?
Maybe just a quick one. What is the prior model? Is that trained on some data set?
Yeah.
Size of that model?
The size of that model is very large. It's like a few hundred millions of parameters, I believe. And it's trained on library speech claim. Library speech, library speech, I remember it has 100 clean, 360 clean, and then the rest is not that clean. So we use that 100 and 360, 100, those things to train the speech diffusion models. But one thing is that the data set, even it says it's clean, it's not super clean, and it's not purely anechoic. Yeah.
No.
So that's that also brings problem, right? And the diffusion model is a time domain unit with attention. So it's from some previous models. We just use it. We just get the model architectures and train on the clean speech data. And later we figured that out. It's the diffusion model is not ideal. And we actually later I did lots of experiments on the better models that can bring up much more performance than all these metrics. The diffusion model we use is it's definitely not fully engineered or optimized in this paper, and we can easily improve it by a lot. Yeah, and one other thing is that all of the diffusion models, they are modeling like fine-grained speech acoustic details. Like even if we have a good one, it's modeling some perceptually good speech, but there's no language content in it. It's not modeling any semantic information because it's all like signal level diffusion model. It's not like latent space or semantic space diffusion model that is able to model like human language speaking and those things. So, you when you sample from the prior, you hear someone randomly talking about some nonsense. Yeah. Yeah. So that's what the diffusion model is modeling. Yeah. And later we had some work on USD on using the same trick for like speech dereverberation, and we are considering like very far field dereverberation. And I'll briefly talk about like what we are doing. And this work is kind of like a combination of lots of existing things. And the key problem is how do we model the room impulse response? And before in ArrayDPS we are using that FCP, and that ArrayDPS also have some dereverberation performance. It's just it's not that obvious. And if you do dereverberation, things are getting more tricky because it's very difficult to calculate metrics. And as we mentioned before, like what is the anechoic clean source that we want to sample? I mean, like we have the clean source and we use it to simulate those multi-channel mixtures. But when we sample it, we're not guaranteed to sample the original one, right? It's definitely shifted and filtered by something. And so how are we going to calculate the metrics? It's quite tricky. And one paper called Body, what it does is that it enforces some constraints so that what you are sampling is on the reference channel, totally aligns with the reference channel. So what they did is that they come up with some RIR model, modeling RIR's magnitude response with a damping exponential decay function. So it's using more RIR properties. Yeah, so some kind of RIR priors also considered. Yeah, and what they do is that in time fixing domain, M is a frame, K is a frequency. Yeah, and H, and this is basically RIR convolving STFT domain, assuming that no frequency leakage, those kind of things. Yeah, some assumptions. And yeah, so H is a RIR in STFT domain, a few frames, all different kind of frequencies. So they define a lot of RIR parameters for this H. One is the phase of the H, and that that would basically like how large your H is. Phi is also that shape, except it's real, it's phase. And the other are the parameters of the magnitude of the H, which corresponds to like the starting energy of a certain band, frequency band. So those K frequency bands, so those K frequency bins are like grouped into B bands, something like that. So each band has a starting energy level, and alpha B is exponential decay factor that says that the IR has to decay by exponentially with some kind of certain speed. And then like A is basically the exponential and some interpolation function of log A prime because we are doing it bandwise for the magnitude. So it has an IR signal model to it. And so when they estimate the IR models, what they do is that they do those gradient descent to optimize the best parameter at each diffusion posterior sampling step. But yeah, and they also did something like when you're estimating the filter, you have to make sure that the first tab is 1 in time domain so that it totally aligns with the reference channel, some kind of those tricks. And so we just directly borrowed the idea for like multi-channel dereverberation. And what we found is that if we define such an IR model for, so one simple solution is to define such an IR signal model for all microphone channels. And that would be very, very messy. It's very slow. And we observe some like the algorithm is not stable because it needs to estimate so many different group of IR parameters. So what we did is that at each time diffusion step, when we need to calculate the likelihood, for the reference channel, we use an IR model and optimize IR using those gradient descent Adam optimizer and get the IR through that. So phi 1, I think it means the it means those IR parameters, like so sophisticated IR parameters for the IR model, and then we can calculate the likelihood loss on that. And for other channels, we just use FCP that we did before, and it's basically finding the best filter that matches in the MMC manner, analytical software directly, and then use that for the filter estimation in the dereverberation, right? And what we have shown is that if for all the channels, if we use FCP, it's not going to work because it's super reverberant conditions, like with RT60 to be more than 1 second, even close to 2 seconds in the data set. And it's also, I think the data is even noisy scenario. Yeah, and we did it anyway. And and what we're proposing is that, if all the channels are using those like sophisticated IR models, it's also not going to perform well, but the performance is good. Right? If we do it something like the reference channel has one IR model and the other channel is just optimized by itself, using FCP, performance is fine and it's much more efficient. And that's some preliminary result on speech reverberation, and we'll present that in WASPA. Yeah, and I'll talk about the limitations of this kind of methods, diffusion posterior sampling, unsupervised method. So they relies a lot on initialization, and so it's definitely one problem of this kind of methods. And but on the bright side, if you look at all the generative models, diffusion-based enhancement, even supervised, you see that sometimes they compare with supervised baselines. But you can see that when they are selecting the baselines, usually the baseline is very weak. They're selecting like a few years ago baselines. They are unable to compare with state-of-the-art supervised baseline. And so what they do to actually compare with the best supervised baseline is that they also, even for supervised diffusion models, they also use a predictive supervised model as initialization. Yeah, so that might be a nature of those generative models. Like by themselves, they are not able to achieve superior performance, and it's always like best to combine one supervised model and one as initialization, and then one generative model on the post processing or something. Yeah, so it's a limitation for our algorithm, but also for like most generative model, like diffusion-based generative model for enhancement separation. And currently, we do not support moving speakers. It needs some more work. For example, the filter estimation needs to be adaptive for convoluted prediction. It's it's still a linear analytical solution, but it's just we need to estimate the adaptively those covariance matrix when solving all of those IR filters. And the last thing is that the computation is super expensive, and many people in the community, they work on device algorithm, and it's and when they look at this and say, like, is this an overkill, right? And it's there are always questions like this, and and we are not sure about that because there might be some actual applications of this, and otherwise it can also just be some academic toys. We don't know. So let's look at the bright side and see like if it's actually applicable and something like that. So first thing is that ArrayDPS allows posterior sampling for any kind of array speech processing problem. So currently we focused on separation, which is a bit easier for multi-channel case. And then we look at the dereverberation, maybe a bit difficult, and then also enhancement currently. That's still a lot of ongoing work we are doing. And it's explainable and controllable in the sense that we can control the trade-off between perception and distortion. And in that paper, what we haven't showed is that it has so there is something that we can control how much we use the likelihood. So there is always like a trade-off between prior and the likelihood, and that could correspond to the perceptual and distortion trade-off. Like if you use lots of likelihood, you are going to get something that sounds very bad, but it will be very have lots of fidelity to the original mixture. But if you have very low likelihood guidance, you are going to get something that's perceptually good. So sounds like the prior likelihood is high, but it might not very much align with the mixture and those things. So there's always this trade-off between perception and distortion, and we are able to control that based on applications. And another thing is that one possible applications is that the algorithm is unsupervised, so it should have much better generalized ability. And there are lots of in the wild real-world data set. And is it possible to use this kind of unsupervised trick to create pseudo labels and train supervised models on those pseudo labels? And I mean, in previous years, many people have tried that with, spatial clustering based those methods. But now we have some new level of methods. So is it have some real world implications because of this? And the last thing is how do we do like real world noise? Basically bringing that to whole speech enhancement, and it's some open problems, and we do have some promising result on this, and we'll hopefully publish more on this. So that's about all. Yeah. Any questions?
Thank you so much. Well, do people have questions in the audience? We actually have a small group, so just feel free to unmute yourself and ask questions. I mean, I have more, but I'll let the audience ask first.
Sure.
Okay, while we are waiting, I might as well just ask.
Sure.
Have you tried, so okay, let's compare your approach to the way, let's say, vision people work on diffusion models. What they do is usually train like a really large prior model and then do some kind of guidance, um, and then kind of learn the correspondence between, the guidance and then the prior, right? And I think you have something like that, right? Remember, you want to approximate the P of X given as tau, that type of thing, right?
Yeah.
I was
Yeah.
just wondering whether you have tried, just do some naive guidance on that.
Like you are saying, like we
Yeah,
directly do
exactly.
this.
Yeah.
We haven't done anything like this before. I don't do this. I never had any experience on this, but I read a lot on this, and a few things is that single channel enhancement, this is almost everywhere.
Mhm.
It's like we feed this X into those we feed X into those diffusion models, and people should sometimes call it classifier free guidance and those things. You can do conditional guidance or classifier free guidance and everything like that. And yeah, but those things like they were never. I feel like they were never a big hit in the whole community. But I do think that but I do see some universal speech enhancement with score model diffusion model. I think it might be from some paper from Dobby that got some attention. That's a very good work. And I feel that what is more like later I feel like there's one paper from Timo Guckman that they do a lot of diffusion for enhancement. So what they did is that so they start the diffusion process not from Gaussian noise. They do it from this X plus some Gaussian noise, and they build a Schrodinger bridge between the clean distribution and the noisy distribution, and that has really good performance in terms of like supervised models. But like one thing is that they don't have that much of there's not that much of experiments or papers on multi-channel. So like we didn't even have a baseline on that. And that's kind of a very open thing in multi-channel, I feel. So, yeah, we should fill that gap, or someone should fill that gap. Yeah.
What questions from the audience? Otherwise, I'll just keep asking.
Oh, I also want, yes, I mean for like vision people, there are also different flavors. It's like there's a whole community of people are working on training free stuff, training
Mhm.
free unsupervised, and you know, uh, Stefan and Stefano Arman and Michael Elad, they work a lot on those like DDRM, diffusion denoising restoration model, and diffusion posterior sampling, IGDM. They work a lot on those things, and and for those models, they focus on like signal level diffusion models, mostly not on latents. There
Mhm.
are also work on latents for that, but it basically most are like signal level diffusion models. So the diffusion model directly models image on like the original clean image. But another flavor is that because people want to have really good perceptual quality and they might not want to have some very full fidelity to the to the observation. So what they do is that they do a lot of latent diffusion, and that can bring up a lot of um, they can bring up a lot of perceptual uh, percep so the quality of the image would be much better. But it's basically the trade-off is that they have to like train different kind of models. It cannot never be training free. It cannot be it's difficult to be unsupervised, something like that.
Mhm.
Yeah, so there's a trade-off between this kind of different flavors of work on diffusion-based processing. Yeah.
Right. If nobody has questions, I will just keep asking. Um, so I feel like when you do this online, well, let's not call it online, but then, when you compute the likelihood, there is an estimation of the filter baked in, right? And that's very
Yeah.
cool, actually. But I also feel like you lost the ability to do um, to just learn from naive data augmentation, right? Because in the supervised approach, people just dump all kinds of RR and just do all kinds of data augmentation, and then just hope the model would be able to infer whatever is learned, right?
Yeah.
And
Yeah.
everything here is kind of on the fly. Um, would it be possible to kind of do something so that this filter can, take advantage of this data augmentation paradigm?
Oh, data augmentation.
Right. So you can kind of have both simulated versus, the inferred one, right?
Oh, I see. It like I'm not sure if we are able to accommodate to like more data set because everything is the only training component in the whole thing is the diffusion part. And itself does not the prior model it does not like take care of any of those it just tries to generalize clean signals. And for the IRs, we are not making any assumptions on it. So basically one way you can say that is that we believe it will work on any kind of IR. Yeah, but it's not going to like fit to any certain distribution of IRs. So like it's difficult for us to consider like data augmentation with different kinds of IR simulated and real world. We believe it will work on like anything, even some IR that doesn't even exist,
Right,
as
right,
long as it's a filter or something like that. Yeah,
right.
it's a bad thing or it's a good thing. It's good generalization, but maybe it's not fully exploited in that level of information. Yeah.
Yeah. I mean, to put it in another way, like the estimation here does not even have parameters, right? So you could have baked-in parameters and then let the model
Exactly.
learn something. Yeah.
Yeah, it's maybe something. Oh yeah. Then yeah, something like this. And yeah, and I remember that my advisor had some crazy ideas. Let's hope he. I'm not sure he will look at this. Yeah, so I remember he had some ideas. He's saying something like this A matrix. It we are doing some blind estimation of the IRs, and is it possible to like forget about estimating those A's as the IR? So forget about this specific problem and focus on any kind of inverse problem. So like any recording, it can be any kind of distortion. It can be from some kind of distortion, from some kind of like a few layers of neural network, some CNN stuck by a band or something, and that will give you the distortion forward function. And is it possible to like generalize to any kinds of possible inverse problems and have a that's related to a neural network? That's maybe that's one direction that's a bit related. Yeah, but it's also a problem about how to estimate those parameters on the fly and things. Yeah. Or are you going to like have some parameters on learning on the fly? It's also possible to have some, you have a that's maybe trained on a lot of different kind of distortions, and you can train some kind of fine-tuning blocks like LoRa, those things, and build on some existing data sets. Yeah, and actually, like some people have done it in image processing community. Like they have a Deft paper called DEFT. Deft. They have done something like, okay, I have a small set of supervised data, and I'm going to train. We are going to train something just to approximate this likelihood model on that data. And the way they train it is quite tricky and novel, right? Because you are not going to train it end to end. I'm not going to backpropagate through 100 diffusion time steps, and they need to find some way to train it. So they have lots of novelties on that, which is super cool. Yeah, and yeah, in those digital imaging community, especially MRI, those people, they have real generalization issues, very, very, very more serious generalization issues, and they also do a lot of those kind of things in on the fly. So for a certain sample, they optimize some kind of system level. They find the best. They even fine tune the diffusion model for each sample, and so that the likelihood is satisfied, something like that. And those things are some of those research out there. Yeah.
Yep.
Yeah, it might be too yeah, too far away.
Right. All right. Well, given that the audience do not have any questions, I guess we'll just thank the speakers again. Thank you so much.
Sure.
Yeah, I'm very happy to have you sharing this. And well, we are having ICAST deadlines very soon, so no more
yeah.
talks for the rest of the month, and we will have more talks in October. Yes. So stay tuned for that. Thank you everybody for coming, and thanks a lot for Zhongweiyang to give the talk. And I'll see you next time.
Sure. Thanks.
Bye.
Thanks a lot. Yeah. See you.